So hello, today we'll be discussing the solar powered home. Now we have three configurations for a solar powered home. Could you guys please read the definitions for the three?
So the first one is grid tied. Grid tied solar power system is connected to the into the traditional electric utility grid. This type of solar power system does not include any storage battery. Next one is the off-grid. This type is a standalone system that is completely disconnected from the electric power grid. It contains a large set of battery packs that store energy during the day to be used at night or a time when sunlight intensity is low. So the last one is hybrid. A grid intertied solar power system is also connected to the traditional utility power grid, which contains a battery backup. The addition of a battery backup enables the system to work when there is a power interruption.
Oh, thank you very much. Now we have grid tied, or what we call the on-grid system. In this setup, the solar PV system is integrated with the grid. The grid is what they call the conventional electricity infrastructure, or the mains. This is the most popular mode of going solar. The features are, it is the cheapest mode of going solar of all the three, and we will still be dependent on the grid. On an average, up to 20% of the energy that we need might still be fulfilled by the grid. Now we have the grid tied with battery backup. This goes a step further, not only with the solar PV system being integrated with the grid, but will also have its own battery backup. Batteries are meant to store excess electricity that gets generated by the solar PV system. Batteries used in solar PV systems tend to be very expensive, hence expect to have the overall cost increase by a significant margin. Now we have the off-grid system. If you live in a remote geographic location, meaning it doesn't have access to a conventional grid, this is the ideal choice. As the name implies, you are completely off the hook of the grid if you opt for this type of system. Here, batteries are a must unless the solar power is combined with other renewable energy resources like wind or a generator. And this tends to involve higher initial investment and installation costs. Okay, so here we have a diagram for the grid-tied system. You can see that even though we still have solar panels, we're still attached to the grid or the main supply. Here are basic parts of the grid system. This is what we'll be focusing on for this discussion. You have the solar panel, the grid inverter, with or without limiter, a square wave or pure sine wave inverter. We'll discuss that later. The DC circuit breakers, DC surge protection device, AC circuit breaker, AC surge protection device, time delay switch, DC-AC electrical wires, MC4 connectors, solar rail, and clamps. We'll be discussing all these later. Okay, so the heart, the solar powered home, a typical solar cell will only produce around half a volt. So by connecting them together in series inside the panel, a more useful voltage is achieved. Now you'll see the standard for the voltages will be 12 volts or 24 volts. And we just connect these in series to get the more desired voltages, such as maximum of 48 volts. Now, most small solar panels rated 150 watt or below are rated at 12 volts, while larger solar panels are 24 volts. A 12-volt solar panel produces around 14 to 18 volts when put under load. This allows a single solar panel to charge up a 12-volt battery. Incidentally, if you connect a voltmeter up to a solar panel when it's not under load, you may well see voltage readings of up to 26 volts. This is normal in an open circuit on a solar panel. This is what we call the open circuit voltage. As soon as we connect a load, however, the voltage will drop to around the specified voltage of 14 to 18 volts. Okay, so could one of you please read this?
Okay, so solar panel connections. So solar panels can be connected together to create a solar array. The output of a solar array is computed much like a battery. Series connections increase the voltage while the current remains the same. Parallel connections increases the current while the voltage remains the same. So when you connect multiple panels together, the power of the overall system increases, regardless of whether they are connected in series or in parallel. Example, each panel on the next slide is rated at 12 volts and 10 amperes. Calculate the following. So first is total voltage, second is total current, and last is the total power.
Okay, so thank you. So as we previously learned in our previous subjects, for a series connection, the current across the cells will remain the same, but the voltage will increase. Now for a parallel connection, of course, the current increases while the voltage should remain the same. Here we have the diagram for the series parallel and series parallel connections of the photovoltaic cells. So as discussed before, 12 volts, 10 amps. So if these 12 volts and amps are in series, we can expect 36 volts and amps as the output from these in series. Now we have these panels in parallel, so we can expect 12 volts, 30 amps from this configuration. Now we have photovoltaic panels in series parallel. For this type of configuration, we can expect around 24 volts, 20 amps. Since two are connected in series, and there are two of those things in parallel. Now we have here another series parallel connection. What we can expect here is again 24 volts, 20 amps. Okay, so now we have the different types of structures that a solar panel has. We have the monocrystalline and the polycrystalline. We have the different factors involving the different build-up of these photovoltaic cells. So for monocrystalline, the silicon arrangement is one silicon crystal, while in polycrystalline, there are many silicon fragments melded together, hence the name. Of course, for the cost, the monocrystalline is more expensive than the polycrystalline. This is because the process used in the monocrystalline is more advanced and involves more work. And for the appearance, of course, we have monocrystalline is black and the polycrystalline is blue. And since the monocrystalline is a newer technology, it's more efficient than the polycrystalline, and it has an expected lifespan of 25 to 40 years compared to the 20 to 35 of the polycrystalline. And it also has a lower temperature coefficient, making them even more efficient in heat compared to the polycrystalline. Here we have a diagram of what we call an inverter. Actually, no, my mistake is a charger, a solar powered charger. This takes the output of the solar panels and connects them up into the batteries or the inverter itself. Could one of you please read?
So the inverter converts the DC output of the solar panel into AC, which is the standard used by all commercial household appliances. Hence, the inverter output matches the voltage within the house that is coming from the grid. But traditionally, there is usually one central inverter in the solar system. A more recent invention has been the microinverter. So microinverters are connected to individual solar panel so that each individual panel provides a high voltage alternating current. This setup is typically used only with grid-tied system. Though costly, they do offer some significant benefits over the more traditional central inverters. So a grid-tie inverter's unique characteristics over the other type is if automatically shut down the system when there is a power interruption.
Okay, so thank you. So forgive me, I was mistaken. This is actually the inverter, the DC inverter. It takes the DC output of the solar panels and converts it into either a pure sine wave or modified square wave AC output. Okay, so now we have the meaning of pure sine wave inverters. Could one of you please read?
Okay, so pure sine wave inverters. So this type of output voltage is in the form of sine waves. Utilities also provide sine wave output. Because of this, pure sine wave inverters are usually needed if you're going to be tied to the grid. Typically, you'll need pure sine wave inverters for sensitive equipment. Use TVs, CFL light bulbs, and appliances with AC motors, such as microwaves and refrigerators. So pure sine wave inverters are capable of producing cleaner, smoother, quieter, and more reliable electricity to operate appliances and electronics without interference. Renogy cells are a range of pure sine wave inverters of varying capacities to fit your solar installation and your energy needs.
So thank you. So what we call the pure sine wave inverters. The pure sine wave is what we'll typically find in our home outlets. This is the same type of 60 hertz sine wave that we can see through an oscilloscope. Of course, we also have a modified sine wave rather, inverters. One of you please read.
So modified sine wave inverters. So in pure sine wave inverters, the AC power produced by the inverter very closely matches an actual sine wave. In modified sine wave inverters, the polarity abruptly switches from positive to negative. When looking at the wave, it has stair-step square pattern where the polarity is flipped back and forth. I love my life that choppy wave can negatively affect more delicate, sensitive equipment. If you have medical equipment, you need power, such as CPAP machine. You won't be able to use a modified sine wave inverter. Additionally, in many cases, you'll hear a hum with devices attached to a modified sine wave that is much cheaper.
Okay, so thank you. Now you'll see that the trend of modified sine wave inverters being much cheaper than pure sine wave inverters. This is because modified sine wave inverters have abrupt changes in the positive and negative loops or polarity shifts that the AC needs. And of course, we cannot use this sometimes in parallel with the mains power of our outlets, since they are not of the same shape and most definitely not in phase. We see here the structure or the structure of the modified sine wave and the pure sine wave. The pure sine wave here is a beautiful looking sine wave that peaks at 120 volts and inverts into 120 volts with no abrupt changes. However, we can see here the modified sine wave goes from 0 somewhere around 100 volts, then flatlines again, then goes to 120 volts, stays there for a few seconds, milliseconds rather, then goes down abruptly again in order to invert, doing the same cycle over and over. That's how we create modified sine waves. It's only an emulation of the pure sine wave. Thus, we cannot use it in conjunction with pure sine wave of our outlets in our homes. Now here we have DC circuit breakers. We use this for the solar panels in case there is a overloading that occurs. Here we have a dual gang DC circuit breaker, and here we have a single gang DC circuit breaker. Here in the dual gang, there's one for the positive and one for the negative, while here we need two for the positive and the negative. Okay, so one of you please read.
Okay, so DC circuit breaker. So the DC circuit breaker, sometimes referred to as the PV disconnector, were placed between the solar panels and inverter, or in some cases, built into the inverter. Just like a typical circuit breaker, it acts as an overcurrent protective device. A short circuit on the part of the solar array may produce a high value of current which might damage the inverter or the system as a whole. Before it happens, the DC circuit breaker acts as an automatic switch, disconnecting the inverter from the solar array. It may also serve as a manual switch if there is a need to turn the solar power system off or isolate the solar panel from the rest of the system.
So thank you. So the DC circuit breaker, much like the AC circuit breaker, acts as a overcurrent protection device. In the event of a short circuit or where the current exceeds the rated capacity of the circuit breaker trips. So this is placed after the solar panel, but before the AC output of the inverter. So somewhere in between that, in order to protect either the photovoltaic cells or the inverter itself. Of course, we also have AC circuit breaker or the RCBO type. One of you please read.
So AC circuit breaker, the RCBO type. So the AC circuit breaker is placed after the inverter. Just like a typical circuit breaker, it's acts as an overcurrent protective device due to short circuits and overloading. So RCBO stands for residual current operated circuit breaker with overcurrent protection. So in the RCBO type, it has added protection since it can sense earth leakage current where the typical breaker cannot. It has stoppability to trip when somebody touches a live wire, thus protecting the people around it. It may also serve as a manual switch if there is a need to turn the solar power system off.
Yes, so thank you. Now, see, in a properly wired up house, we have 3 wires, right? A live, a neutral, and a ground. Now, if the AC circuit breaker RCBO type detects a current, a minimum current of maybe 4 milliamps, it depends on the RCBO. If it detects that current between live and earth, then it trips, thus protecting whoever or whatever connects the circuit between those 2 lines. Here we have the RCBO, a dual gang. Looks much like a normal circuit breaker. Now, here we have the DC SPD, which is placed in parallel with the DC circuit breaker. SPD generally protects the system from power surges, or more appropriately called voltage transients. SPD redirects this excess power to the ground. In a PV system, since solar panels are heavily exposed to the environment, transient voltage is primarily caused by lightning, either directly or indirectly. Multiple interconnections within power cables are very susceptible to electromagnetically induced transient, where power surge could also arise. Transient voltage is the occurrence of very high voltage in a very short duration of time, around tens to hundreds of microseconds. Exposure to transient voltage may cause catastrophically component damage, leading to system failure. We also have an AC surge protection device, much akin to the DC surge protection device. We have the gang one. The live wire goes here and the neutral wire goes here. And of course, we need an earth line for in event of transients. So the transient voltage has somewhere to go. We have another example of the AC surge protection device. And once again, 3 types of 3 terminals, DC positive, negative, and ground. We have another example, of course. You can see transient voltage is 20 kiloamps. Transient current rather of 20 microseconds, 20 kiloamps. And it's rated for 600 volts. Okay, good. Now we have the AC surge protection device. One of you please read.
Okay, so AC surge protection device. The AC SPD is placed parallel to the AC circuit breaker. Just like the DC SPD, this serves as protection against transient voltage, but this time on the AC side of the PV system. SPD redirects this excess power to the ground. Multiple equipment connections on the grid, either internal or external, can also be a cause of electrical anomalies where power surges could also arise.
Okay, so thank you. So this is basically much akin to a DC surge protection device. It basically serves the same purpose of redirecting transient voltage from the AC side this time to ground. We have a picture of such a device, a time delay switch. We have the meaning of the time delay switch. So Navi, please read.
So a time delay switch, this can be called a power on delay. It delays the turning off of any electronic device for the desired time interval. So this device serves its useful purpose usually when brownout occurs. So after a brownout, when power has already been restored, there is the tendency for a power surge which may cause the damage the system if it is being turned on right away. So to prevent this, the time delay switch delays the turning on of the system for a minute or even a bit more.
Okay, so thank you. So now in the event of a power outage, right? If the power comes back on and all the devices were not turned off, there could be a possibility for a surge since all the devices will be trying to have a what we call inrush current all at the same time. This could lead to a surge. The time delay switch prevents that from happening. It delays the power to a certain device or a certain power outlet or a certain circuit by a predetermined amount of time in order to prevent such a surge from happening. We also have here a more advanced timer switch, a programmable type. This programmable timer switch, turning the solar power system on and off could be a vital routine that cannot be perfectly done in a day-to-day basis. Programmable timer is a hassle-free switch to automatically turn the system on and off at the desired time. Okay, now we have the net metering. Now, what is net metering? One of you please read.
Okay, so the net metering frequently asked questions. So number one, or question one, what is net metering? So net metering allows customers of distribution utilities to install as on-site renewable energy facility not exceeding 100 kilowatts in capacity, so they can generate electricity for their own use. Any electricity generated that is not consumed by the consumer is automatically exported for the distribution utility system. The DU then gives a peso credit for the excess electricity received, equivalent to the DU's blended generation cost, including other generation adjustments, and deducts the credit earned to the customer's electric bill.
So thank you. So basically, if you have, for say, a excess of solar power, you can use this excess solar power to pay off your electric bill or even earn money. This, of course, it requires a lot of clearances and forms that needs to be filled out. But it is a useful tool in order to earn more money from your solar array. Now, is net metering already available in the Philippines? Well, on May 27, 2013, the Energy Regulatory Commission, ERC, Resolution number 9, series of 2013, approved the rules of enabling the net metering program for renewable energy. This resolution was published on July 10, 2013 in newspapers of general circulation in the country and took effect 15 days thereafter. Thus, net metering rules took effect in the Philippines on July 24, 2013. The net metering is available only to the on-grid distribution system or DUs connected to the transmission grid. Now, what benefit will I get if I go into net metering? Could one of you please read?
So by generating electricity for your own use, you can reduce the amount of electricity you can buy from your local DU. So the rate of savings or avoided costs are system loss realized on electricity generated for own use is equivalent to the DU's retail rate, consisting of charges for generation, transmission, distribution, subsidies, taxes, and other charges. So you also earn per peso credits on any excess electricity exported to the DU equivalent to the DU's blended generation cost. Excluding other generation adjustment, the peso credits earned are then used to reduce your electric bills.
Okay, so thank you. So as mentioned before, the excess power that you generate from your photovoltaic system can be used to provide the grid, thus earning money in peso credits, which can reduce your bill further. Okay, so now how will my DU meter import or export energy? The DU may operate to install unidirectional meters, one to meter energy that we buy from the local DU, and the other to meter energy you buy, and the other meter to meter the energy that we export to the DU. The DU may, at its options, install a single bidirectional meter that can meet both import and export energy if it finds it to be more economical. The DU may also install a third meter in proximity to the RE facility to meter its local RE generation. The total RE generation shall earn for the host DU RE certificates, which the DU can use to comply with its renewable portfolio standards obligations. So these are basically specific cases which the DU is choose from in order to monitor what energy we import and export. Now, who is qualified to participate in this net metering program? One of you please read.
So, DO customers who are in good credit standing in the payment of their electric bills to their DO are qualified to participate in the net metering program for renewable energy. Those customers are referred to in the rules as qualified end users or QE.
So as long as you're paying your bills on time, you'll be qualified end users. Now, of course, we have consequences of not applying for net metering. Could one of you please read?
So one of the consequences of not applying for net metering, so in the case that a solar power system is being installed and doesn't apply for the net metering, any excess energy that is being fed to the grid will be billed to the customer. For example, when the system is rated at 5 kilowatts and the load consumption is only 4 kilowatts, the system will have an excess of 1 kilowatt rather, which will be sent to the grid. This excess energy will pass through the meter and hence will be billed to the owner.
Okay, so thank you very much. Now, if you don't set up the net metering properly, or you don't bother messing with your meter, if you say have a 5 kilowatt in this example right here, 5 kilowatt rated, but your load consumption is only 4 kilowatts, then you have an excess of 1 kilowatt that will then be fed back into your unmodified meter, but will still be read as power that you consumed. Thus, you will be billed for this 1 kilowatt. Okay, so now another question is there any other way besides net metering that the customer has a solar power system producing excess energy during the day and yet will not pay for it? Well, of course, this can be achieved using an inverter with a limiter. This device limits the power that the system will dissipate. It automatically detects the maximum power that the system can provide without the excess being sent to the grid. Okay, now we have the diagram, the main diagram for this grid tie inverter, the circuit connections. First, we have the solar panel, the main attraction of the show, with its outputs going to the master circuit breaker or the DC side, and then it goes to the charge controller. This charge controller goes into the DC output of this charge controller goes to the battery, which is in series with another master circuit breaker for DC. Now, this charge controller also goes to another DC load here, but the DC output can also go into an inverter. The inverter now inverts that DC into either pure sine wave or modified sine wave AC and steps it up to the proper voltage required by the system and passes it along the AC outlets of our homes, powering the AC loads such as our devices such as TVs and electric fans. Okay, now we move on to wire sizing. We have the thermoplastic wire, TW, moisture resistant and flame retardant. Of course, we also have thermoplastic heat resistant wire, THW, which is moisture resistant and flame retardant. And you see the diagram picture. Then we have also THN, which is thermoplastic high heat resistant nylon coated. This is designed for specific insulation material, temperature rating, and condition of use, suitable for dry and damp locations. Now, we also have THHN or THWN-2. Now, THWN is similar to THHN, except it is water resistant, adding the W into the acronym, of course. THWN is rated for up to 167 degrees Fahrenheit or 75 degrees Celsius in wet environments, but its successor, THWN-2, is rated for 90 degrees Celsius in both wet and dry environments. Historically, THHN and THWN were separate wires, but now you'll typically find their capabilities combined in the THHN/THWN-2 design. Now, note, here's a breakdown to help make some sense of the lettering. The T stands for thermoplastic, insulated cable. A, single H in the wire means it's heat resistant. Double H means that the wire is heat resistant and can withstand a higher temperature. The added W signifies that the wire is also resistant to water. Now we have PV wires. This type is an exclusive kind of wire rated for PV applications. These cables behave extremely well in hot temperatures and other harsh environmental conditions. Its special characteristics compared to other wire is its insulation and outer sheath, which is made up of XLPE or EPR. XLPE is an acronym for cross-linked polyethylene. XLPE is a thermosetting polymer, meaning that the material, polyethylene, PE, is cured under heat, and in that process forms bonds in all directions, forming a three-dimensional matrix. EPR means ethylene propylene rubber. We have the American wire gauge. You can see here that it's not very intuitive because as the numbers go down, the wire size actually gets bigger. See here, 12 AWG is actually significantly smaller than 0 WG. Now, of course, it does not end with 0 WG. There's 00 AWG and I believe 000 AWG. Now here we have the table for allowable ampacities of insulated conductors rated up to and including 2000 volts from 60 degrees Celsius through 90 degrees Celsius. Now we'll be coming back to this table later and we'll be using its values later. Now here we have the AWG, circular mils, square inches, square millimeters, and of course weight and the overall diameter. We'll also be using that table later. Now we have the ambient temperature correction factors based on 30 degrees. Now if our environment is not 30 degrees, greater or below 30 degrees, we'll be using correction factors present in this table. We'll also be using it later since the ambient temperature of the Philippines is 37 degrees Celsius. Here we have another table for the ambient temperature adjustment for circular raceways exposed to sunlight on or above rooftops. Okay, now we have okay, so now we have the steps in calculating the conductor sizing for the PV system. Okay, so could one of you please read the first 5 steps?
So, okay, so first step is look for the ISC rating of the PV cell. Second step is multiply by 2 safety factors, which is irradiance and the continuous duty. Step 3, refer to the table 310.15b 16 for the size of the wire. Step 4, refer to table 310.15 B2A for ampacity correction due to ambient temperature of more than 30 degrees Celsius. 5. Refer to table 310.15 B3C for ambient temperature adjustments due to the conduit or wire distance from the roof.
Okay, so thank you. So now we first need to look for the ISC rating or the current short circuit rating of the photovoltaic cell. We'll be having an example later for these steps. Now we multiply the ISC by the irradiance and continuous duty. Then we refer to the table I showed earlier for the appropriate size of wire we guesstimate. Then we multiply that for ampacity correction if the ambient temperature is more than 30 degrees Celsius. Then we also adjust for the ambient temperature adjustment due to conduit or wire distance from the roof. Okay, so could one of you please continue?
So the next step was refer to the table 310.15 B3A. So for adjustment due to more than 3 wires inside the conduit. So moving to the next step, find the adjustment due to voltage drop. So after that, the value obtained in the last step will be the basis for the size of wire to be used in the PV system.
So thank you. So in step 6, we have an adjustment if we have more than 3 wires in a conduit. Now for step 7, we find the adjustment due to the voltage dropped. We'll be having a formula for that later. And then step 8, the value obtained in the last step will be the basis for the size of wire to be used in the PV system. So now let's have an example. Here I have a Sharp ND224UC1 224 volt solar panel specifications. Here we see that the ISC is 8.33 amps. So now we'll take, for step 1, we'll take that 8.33 amps and we'll take note of that as the IPV. So for step 2, we multiply by the 2 factors. So the IPV new is 8.33 times 1.25 times 1.25, which is equal to 13.02 amps. We'll take note of that 13.02 amps. Okay, so now we take a look at the table from before. Let's go back to the table. We can see for the copper, we have THHN. We have number 16, which is 18 amps. Let's see. Number 16, THHN with the ampacity of 18 amps. So we'll use that for now as an estimation. Now, step 4, we correct for ambient temperature. Since the Philippines ambient temperature is 37 degrees Celsius, we use the table again. This table. Here's the table. This part of the table right here, 37 degrees. Around here, we multiply for this THHN, multiplicity factor of 0.91 here. Okay, so now we multiply that 18 ampacity of the number 16 THHN wire with 0.91, and we get 16.38 amps. Okay, so now we have the ambient temperature adjustment due to roof wire distance. For 1/2 in the above roof, we have the ambient temperature plus 22, we have 59 degrees Celsius. Now from the previous table again, we multiply the previous value that we got, 16.38 amps, by 0.71. We got that 0.71 from this table right here, 0.71. And now we get 11.63 amps. Now, take note that 11.63 amps is less than our previously calculated IPV new of 13.02 amps. So our selected number 16 wire will not fit the system. So let's repeat the steps. This time, let's go for the number 12 with an ampacity of 30 amps. Now we repeat the previous steps. For the step 4, for the ambient temperature ampacity correction, 25 times 0.91, 27.3. Step 5, 59 degrees again, 27.3 times 0.71, we have 19.38 amps. Now we can see here that 19.38 is greater than 13.02. So the number 12 will fit the system. Now then, for step 6, since there are only 2 conductors in the conduit, we don't need to do anything, thus the step is bypassed. Now for step 7, adjustment due to voltage drop, we'll say around less than 3%. Of course, this is varying depending on the conditions. We use the formula of VD equals 2 times IR, where R can be K. This is a DC, is the direct current constant multiplied by the length and the area. Length in feet and area in circular mils. So now we have the VV 2 times 8.33, which is the ISC. The IP. The current of the photovoltaic cell times 12.9 K times 25 over 6530. Now 25 will assume that that's the length that we'll be using, and 6530, that's the area in circular mils. We can see the area in circular mils from this previous table right here. Since we have a number 12 AWG in circular mils, that is 6530. So that we just plug in that value into the equation, and we're left with 0.82 volts. Now we find the percent of voltage drop, so we divide that by the voltage of the cells, the photovoltaic cells, times 100%, and we get 2.79%. How now? Since 2.79% is less than 3%, the selected 12%, number 12 wire will fit the system. But since 2.79 is a bit near to 3, it would be better to use the number 10 THHN wire for additional safety factors, and of course, if we want to expand in the future. On the previous problem, in case the voltage drop exceeded 3% to let's say 5%, the additional computation is as follows. Since the initially selected wire is number 12 THHN, makes a one-step higher adjustment, select initially number 10 THHN. So we make the previous calculation for the voltage drop again. We get 0.52 volts. And for the percent voltage drop, we just divide that again by the voltage of the photovoltaic cell, but times the 100%, and we get 1.77%. So the selected number 10 THHN wire will be the final wire to be used in the system. As I said before, the K is a direct current constant, which is the constant representing the direct current resistance for 1,000 circular mils conductor that's 100 foot long at an operating temperature of 75 degrees Celsius. The direct current constant value you should use for copper is 12.9 ohms. That's where we got the 12.9 value from before. And 21.2 for aluminum. The K constant is suitable for alternating circuits where the conductor does not exceed number 1 or 0. So now we have DC circuit breaker sizing. First thing to consider in sizing a circuit breaker for a PV system is the ruling in the Philippine Electrical Code, which states that a PV circuit current is continuous. Thereby, the minimum OCPD rating is 125% of the maximum current. The PEC 2017 Article 6.9-.2.2b and Article 6.9.2.3b. Therefore, in reference to the problem in conductor sizing, on the DC side, the max current is 15.23 amps multiplied by 125%, which is a 19.4% USE 25 circuit breaker. On the AC side, let's assume that the inverter rating is 1.5 kilowatts and a current of 12 amps multiplied by 125%, that is 15. We use a 20 amp circuit breaker. Now we have the SPD sizing. Now the rule is simple in sizing of the surge protection device. Basically, the UC rating of the SPD should match the system voltage, or of course be a bit higher, with around 15% to 25% for SPDs to attain longer lifespan. Therefore, in reference to the problem in conductor sizing, for the DC side, use SPD with a UC rating of 100 to 120 volts. For the AC side, use SPD with a UC rating of 230 to 275 volts. Of course, we have now the SPD specs. The in is the nominal discharge current. This is where the SPD will be living most of its life. The expected amount of current will be normally discharging. The maximum current, the Imax. The UC, the maximum continuous operating voltage. The UP, the voltage protection rating, VPR, or surge voltage rating, or clamping voltage. So now we have the zero bill computation. Compute for the monthly average of kilowatt hours used. Let's say 300 kilowatt hours per month. Now we convert the daily usage of 300 kilowatt hours per month. Now 30 days is equal to 10 kilowatt hours per day, which is equal to 10,000 watt hours per day. And peak sun hour, PH sun hours, which is 5 hours a day, the solar array rating would be 10 times 5. It's equal to 2,000 watts. For zero bill assurance, 2,000 times 1.1 is 2,200 watts. Number of panels, 2,200 divided by 300 is 7.33, which is 8 solar panels. Wait, no, I'm sorry, 10,000 divided by 5, that's 2,000 watts. Okay, so that's all. Thank you for listening.